section. It's actually the last section in the taking derivatives section of this class. This section is going to talk about the tangent line. We've talked about the tangent line before, but it's been very abstract. And we talked about the slope of the tangent line, which is the derivatives, but we haven't really explained like what it actually means and what the tangent line is and what that does so far. Okay, so let's start. We're going to start this thing called linear approximation, which is the dumbest way of saying looking at the tangent line. Okay. There's a lot of notation here, which I don't think is very interesting, but we'll talk about what it actually means later. Okay, but before we talk about linear approximation, we're going to do something that I think a lot of calculus teachers do while they introduce derivatives. I do this in this section just because I think it makes a little bit more sense. But we're actually going to find how to find the tangent line at any point of a function. Okay, now we know that the tangent line is this thing that barely touches the function. It only touches the function at one point, and it kind of like grazes our function. We know that the slope of the tangent line is the derivative at any point, right? And that's pretty much all we know about the tangent line. Let's actually go over how we find the tangent line and a process on how to get this function actually, okay? So if we want to find the equation of a tangent line, the first thing we're going to do is we're going to find the derivative of our function. The derivative is the slope of our tangent line. So that would be pretty useful for us to get our tangent line, right? All right. The next step in finding our tangent line is we're going to plug whatever point that we're interested in into our derivative. Okay, so we're actually going to find the point or a value of our slope at the value that we're interested in. We're also going to plug x into our original function to find an x and y point. Okay, now once we're at step 3, we have the slope of our function. We have a point that we're of our line. We can plug that into this thing called the point slope form of a linear equation. I actually don't like point slope form, but it is kind of useful here. So we're gonna have this equation here. We're going to plug our values into this function here, and it will give us the equation of our line. Okay, now this is an equation that I really do want you to know or memorize. I think a lot of you had to memorize this in a algebra class before. Yeah, so let's just go on and see what we can do. Okay, so we want to find the equation of the line tangent to x cubed plus the square root of x at x equals 4. Let's go through the steps and see how this actually comes out. Okay, now step 1 is to find the derivative. And it's honestly kind of hard to find the derivative of a square root. What's another way to write the square root of x? X to the 1/2, good. Okay. Now that I have everything written out in powers, can someone tell me the derivative of x cubed plus x to the 1/2?
3x squared plus 1 over 2 square root of x to the 3rd.
Nice. I like that. I'm actually going to go a little bit slower than that, but the derivative of x to the 1/2 is 1/2 x to the negative 1/2, right? All right. And then if I put this in a better form, it'd be 3x squared plus 1 over 2 square root of x. Okay. So just found my derivative. That's good. Okay. Step 2. Step 2 says plug x value of the indicated point into f prime of x to find the slope at x. Okay, so I want to find the slope of the tan line at x equals 4. Okay, so essentially what I'm doing is I'm plugging 4 into the derivative. So 3 times 4 squared plus 1 over 2 square root of 4. Plugging it into f prime. Okay, now let's see if I can do this in my head, but probably not. I'm going to cheat a little bit. 4 squared is 16. 2 times the square root of 4 is 4. So you can check me on this, but I think I'm getting 193/4. Okay, this is my slope of the tangent line that I want to find. Okay, so once I'm here, guess I got to go to step 3. Step 3 says I don't want to I don't just want to know the slope at x = 4. I want to find what the actual function does at x = 4. Okay, so I'm going to plug x = 4 into my original function. So I'm plugging x = 4 into y = x³ plus the square root of x. Okay, so this becomes 4 cubed plus the square root of 4. And that's 8 plus 2, right? Which is, no, that's not true. 4 cubed is not 8. What's 4 cubed? 64. Okay, good. 64 plus 2. That looks a little bit better, doesn't it? Okay. So let's just kind of step back and see what we did here. We found the x value and y value of our function at that point. So we have a point of our function that we know the tangent line goes through because it hits that point. And we also know the slope of our tangent line. That's all the information we need to make our equation of a tangent line. And the way we're going to do that is to plug it into this point slope equation. Okay, so we have y minus y1 equals m times x minus x1. Okay. What do you think y1 and x1 are?
66 and 192.
Yeah, that's the actual point of that we're going through, right? So I know that x is x1, y = 66 is y1, and the slope of the tangent line is always going to be m, right? M always talks about the slope. Okay, so plugging everything in, it looks like we have y minus 66 equals 193/4 times x minus 4. Okay. All right. Once we're here, I do like getting y by itself. I'm not going to simplify too much because sometimes making an equation is easier if, or graphing equation is easier when we do this. But I'm going to add 66 to both sides just to get y by itself. So 193/4 times x minus 4 plus 66. Now, of course, you can distribute the 193/4 to the x and the 4 and add them together. But for some reason, the textbook uses this notation. So let's just keep it like this and not do anything more. Okay, so what I just found here is the equation of the tangent line at this point. And the point is 466. Okay. Okay, before I talk about the graph real quick, I just want to recap what we just did in terms of our final answer. What we did is we found the derivative, and we found the derivative at the point. Okay, so this is f prime of our point 4. Okay, we put the x value that we're interested in next to the x, and we also added on the y value, so f of 4. Okay, now the point slope equation is always going to have this certain form. I do want to point this out just so when we get to an actual equation of our linearization, you'll see what's actually going on. Okay, before we go forward, I just want to show you what this actually looks like. Okay, in this very badly drawn graph here, the curvy function is our y function. Okay, that's actually the function of x³ plus the square root of x. Okay, and the straight line that's almost touching the function is our tangent line. So this is the tan line, which is the like 193/4 function. Okay, and where it touches the function is our point, which is 466. Okay, Now, not very illuminating, but what we're actually going to do in this section is we're going to think about what the function does or what the tangent line does really close to the point that we're interested in. So we're actually going to think about what happens near 4 comma 66. Okay. Now I know you can't do this on your paper, but if you zoom in really, really, really close to my point at x equals 4, what can you say about the tangent line compared to the function? So maybe like around, like if I looked at x values really, really, really close to x equals 4, what can you say about the tangent line compared to my original function?
They look the same.
Yeah, right? My tangent line looks very, very, very close to my function. It almost like matches the function near those points. Now, as we zoom further out, the tangent line does look a lot different than my original function, but really close to the point, the tangent line does pretty much approximate the function, okay? We'll come back to this, but I do want to have you get a little bit more practice with finding the tangent line at a specific point. So if you flip over to example number 2, I have another example for you. I want you to find the equation for the tangent line of 7e to the x plus 3. Okay. So I need to get Daniel. I would ask someone to write this up, but I do want to go over the step-by-step way just in case we're following that in class. So let me just go through steps 1 through 4. I know a lot of you were able to do this in your head, which is good, but I don't know why. I like the steps a little bit better. And for some reason, I can't move this chair. There we go. All right, let's go through these steps. I said that step 1 was finding the derivative, and I don't know why I changed this. So step 1 was finding what y prime was. What is the derivative of 7e to the x plus 3?
70.
7e to the x, good. Okay, so step 1 is done, I found my derivative. Step number 2 is to find the slope at my specific point. So I want to find slope of the tangent line at x equals 0. And what that's telling me to do is to plug in 0 into my derivative, right? So I'm going to plug in 0 in for x. Okay. What's e to the 0? 1, right? Anything to the 0th power is 1. So 7e to the 0 is actually 7. Okay, so I know that my slope is 7. Step number 3 is to find not just the derivative evaluated at 0, but my original function evaluated at 0. So I want to find my OG function, or original function, evaluated at x equals 0. Okay, which means I'm plugging in 0 in for x up top. Okay, now we already said that e to the 0 is 1, so 7 plus 3 is 10. Okay, so in my point slope equation, I know that x1 is 0, y1 is 10, and m is 7. Okay, so going on to step number 4. Okay, plugging into point slope, I'm going to get, let's see, y minus 10 equals 7 times x minus 0. Okay, getting y by itself, this becomes 7 x minus 0 plus 10. Of course, you can get rid of the 0, but I'm going to kind of not do that yet, just so we have a correct form here. Okay, so slope of my tangent line is this. I know it looks weird, but just bear with me here. Okay, going through this again, 7 was f prime at a or 0. Okay, I have my x value or 0 here, and I'm adding on f of 0. Okay, I know that sounds weird why I'm saying that, but I promise I have a point here. Okay, before we go into generalizing this, let's just take a look at the graph here. Okay, So the graph that I have, the curvy line is my original function, y, okay? This dotted line is my tangent line. Okay, and I wanted to find the tangent line at x equals 0. So the point that I was interested in was 0, comma 10. Okay, now let me just do the same thing as I did in the last page. If I zoom in real close to my function at x equals 0, the tangent line does still look very similar to my function around that point. So right here, between these 2 points, it looks like the tangent line and my function are about the same function. Now, it's not really that apparent as we zoom out. The tangent line is definitely a different function, but as we get really close to my point, the 2 functions are pretty much the same. Okay, so we have a name for this. Since my tangent line is very close to my function at a specific point that I find my tangent line at, we actually have a different name for the tangent line. We call it a linear approximation. Okay, so let me write that out. Linear approximation. And we call it that because the tangent line is linear, right? It's a linear line, and it approximates the function at a specific x value. Okay. Okay. Here we're going to get to a very stupid definition. Textbooks love to define things, put names on things, and make you memorize formulas. Okay. But basically, we have this thing called the linearization. Okay. We call it L of x. We call it the linearization, but it's a very dumb formula because it really is the equation of the tangent line. L of x is f of a plus f prime of a times x minus a, which is literally what we've been doing in the past 2 examples. Okay, so you can memorize this formula, okay, or you can just know to find the tangent line and solve for y, and that's your linearization of a function. Okay, so this is the tangent line. Okay. And then the textbook throws another equation at you. The linearization or the tangent line approximates the function at a specific point. So near that point, we can say that our original function is very close to the tangent line near x equals a. Okay, so this is all it's saying. I know there's a lot of symbols floating around. All this is saying is that my function is very close to the tangent line at my point. Okay. Any questions so far? All right. Let's go to the next page and see what types of questions we can be asked when we're dealing with this. So let's just go through example number 3 here. Okay. So example number 3. We want to find the linearization, which is just the tangent line equation of this function here at a equals 1. And we want to use this to approximate 2 numbers. Okay, so this question is asking us is to find these numbers or approximate what these are without using our calculator. And we want to figure out if these are good estimates. We want to see if it's an overestimate or an underestimate. Okay, so I guess what we have to do is we have to find the equation of the tangent line of this function f. Okay, I'll do it the textbook way of finding using the formula. You can also just find the tangent line. Okay, so I guess what we have to do is find the derivative. That sounds about right. We're in a calculus class. Okay, now it's kind of hard to find the derivative of a square root. Of course, we went over this earlier today, but we can write a square root as something to the 1/2 power. Okay. What sort of rule do you think I'm going to use to find the derivative here?
Square.
Yeah, the chain rule, right? Good. We're going to use the chain rule for this. Okay, what's my inside function? Good. And my outside function is the 1/2 power, right? So the outside function is my square to the 1/2 power. Okay. So when I find my derivative, what's the derivative of a box to the 1/2 power?
The negative 1/2 x.
Good, 1/2 box to the negative 1/2. Okay, so that's the derivative of the outside using the chain rule. What's the derivative of my inside function? 1, not x, but 1, right? Okay, good. The derivative of x is just 1. Okay, well, completed my chain rule. I guess I can write the inside function on the inside of the box. And just cleaning things up real quick, it looks like we have 1/2 square root of x plus 3. I know I skipped a couple of steps there, but this is our derivative of my function. Okay. All right, that was step 1 of finding the equation of the tangent line. Let's just find the equation of the tangent line evaluated at my a value. Okay, since a equals 1, maybe I should start plugging a into things. Okay, well, that's just plugging 1 into my derivative. 1/2 square root of 1 plus 3. Okay, 1 plus 3 is 4. So I think this gives me 1/4. Okay. Now remember, step 3 of finding the tangent line equation is to find my function evaluated at 1. So not just plugging 1 into the derivative, but also plugging 1 into my original function. Okay. This is the square root of 1 plus 3, which is 2. Okay. So I know this is a lot that I just wrote down here. I found my function. Let me make this a little bigger. I found my derivative. I evaluated the derivative at 1, and I also evaluated my function at 1. Okay. Any questions so far? Okay. The final step is to use my point slope equation to find the equation of the tangent line. I'm going to actually use the textbook method here just so we have 2 different ways of doing this. But the textbook tells us that we have this formula, right? L of x equals f of a plus f prime of a times x minus a. Okay. Now, this is essentially the equation of my tangent line, but of course the textbook likes to put names on stuff. Okay. Well, I evaluated f of a, and that was 2. Okay, so that was found in the pink highlighted area. Okay, I know that f prime of a is 1/4 because I found that in purple. Okay, and we have x minus a, and I know that a equals 1 because the question gave it to me. So I know that 1 is here. Okay, so 3 different values I'm plugging in to my L formula. Okay, I guess we can clean this up a little bit, right? I can multiply the 1/4 over to get 1/4 x minus 1/4. And correct me if I'm wrong, but I think this gives me 1/4 x plus 7/4. Okay. So what I just found here is the tangent line equation, or in the textbook's terms, the linearization of my function at a equals 1. Okay. Now what this is saying is, I have my function, and I know you guys are still writing, so I'm going to give you a little bit of time to do this. Okay. Went a little bit fast here. All right, going down to my equation or my graph, I know that the original function is here in blue. Okay, so this is my original function. The straight line is my tangent line, right? So this is the tangent line, which we also called the linearization. Okay, now we evaluated this function, or we evaluated the tangent line at this point 1, 2. And I know that if I zoom in really, really close to my function at x equals 1, the tangent line is very, very similar to the original function. Okay, so if I plug in points near x equals 1, I'm going to get something very close to my original function. Okay, all right. Let's figure out what we can do with this linearization. Okay. Well, the function says, or sorry, not the function, the question told us to approximate two numbers, okay? So I'm going to approximate the first one. And I'm gonna, we're gonna write this down. We're gonna write that we're evaluating the square root of 3.98. Now, I know that you can do this in your calculator by just taking the square root of 3.98. Let's see if we can approximate it using linearization. Okay. Now, here's where things get a little confusing, and this is why I'm going to rewrite this question in a slightly different way. Okay. If I want to approximate this function, this is the same thing as saying this. I want to approximate 0.98 plus 3. Does anyone see why I rewrote 3.98 as a sum of two different things? So why did I break this up into 0.98 plus 3?
Maybe one things would it be easier to take this?
Not quite.
Looks like the original function.
Yeah, okay, so John said, look at the original function. My original function is the square root of x plus 3. If I do this, now I have something plus 3 with a square root. This looks like, so the reason, oh shoot. The reason I did this is because this looks like my original function, which is the square root of x plus 3, okay? Now, when I write my number like this, it's very easy to figure out what x equals. What is x equal in this equation or in this number? 0.98, right? Okay. So if I want to approximate what my function is to get the square root of 3.98, all I have to do is plug in 0.98 into my function. Okay. Now, I'm not going to plug it into my original function because that would give me the exact answer. To approximate my function, I'm going to plug this in to my linearization. Because the linearization is the approximate function. Okay. So let's do that. L of 0.98 is 1/4 0.98 plus 7/4. Okay. Now you can do this in your head if you want, but I'll save you some time. And this actually gives me 1.995. Okay. So I found my approximate value of the square root of 3.98. Okay. Let's actually just compare that to what 3.98 is. If you ever go in your calculator and figure out what the square root of 3.98 is, you're actually going to get this, 1.99499. Okay, so that's the actual value of the square root of 3.98. What I found here is the approximate value. And as you can see, it's very close. It's just rounded to 3 decimal places. So this function actually does do a good job of approximating the square root of 3.98. Okay. Now I know this sounds kind of dumb because we have calculators that can do this very fast. But imagine if you had a calculator that didn't or wasn't able to find the square root. Okay. Instead of doing a bunch of work to find the square root of 3.98, you could find the linearization and plug it into your calculator and get something very, very similar to the square root of 3.98. Okay. Now the question says, is this approximation an overestimate or an underestimate? What do you guys think? Yeah, so you said, okay, it is an overestimate, right? Because 1.995 is bigger than the actual value 1.99499. So you're like, okay, it's an overestimate. And why do you think everything's going to be an overestimate? Well,
If it curves, it has to curve away.
and look at the graph. My tangent line or the approximate function is always over the original function, right? This function is above the original function. So any approximate value is going to be above the blue line, okay? So actually, my approximation is always going to overestimate my function in this example, okay? All right. Any questions so far? Okay, let's just answer the last question here. We want to approximate a different value here. So part 3 is to approximate not the square root of 3.98, but the square root of 4.05. Okay. What am I plugging in for x here?
0.5 or 0.05.
Not just 0.05, but 1.05. It's +3, not +4.
Oh.
You're good. Okay. The way I got that is I know that 4.05 is 1.05 plus 3. Now that I know this looks like my function, x would be 1.05 and 3 is part of my function. Okay. So plugging it into my L function, that gives me 1/4 times 1.05 plus 7/4. And I'll save you some calculations here. I'm getting 2.0125. Okay. Let's compare that to what the square root of 4.05 actually is. Okay. So if you ever do this in your calculator, find the square root of 4.05, you should get 2.01246. Okay. All right. Well, comparing these two, do you think this is an underestimate or an overestimate?
Over.
The approximation is actually, I think it's bigger, right? So this is bigger than 2.01. So this is actually an overestimate. Okay, now we predicted everything would be an overestimate, but now we actually have it kind of proven for us. Okay. Any questions on example number 3? All right. I want to talk about something. Yeah, I do want to talk about this. Okay. If we flip over to the next page, what I just did is instead of showing a graph version, I have a table that might make this make sense a little bit more. I think we're all on the same page that the linearization approximates the actual function. But let's just go over what this table says. Okay. So in this table, we know that we're approximating the square root of x plus 3 near x equals 1. Okay, so at x equals 1, the approximation L of x actually equals the function value, and that actually always happens. So at the point that we're looking at, the approximation and the actual value will always match. Okay, as we get further from our value A, or what we're plugging in, the approximation gets a little bit worse. Okay, so we did 0.98 and 1.05, and these approximations were very good approximations. As we get further and further away, for example, if we plug in x equals 3, the approximation isn't as good. Okay, if we plug in a value like x equals 7, you would see that the approximation is really bad. But close to my function, the approximation is pretty good. Okay. Let's take a look at example number 4. I have to put in trig functions, right? So I'm going to give you a few minutes to find the linearization of sine of x at x equals 0. And I also want you to use this to evaluate sine of 0.01 and sine of negative 0.01. Right. Let's come up to the front here. I got John to write up how he got the linearization function. Do you kind of want to take us through your steps here?
So I just found the derivative equation, first step.
Mm-hmm.
The second step, I plugged 0 into the derivative to find the slope. Plug 0 into the original function, define its x and y values, set that up in the slope formula, and then simplify it.
Perfect. So you got your linearization function. Let me talk about how we do the approximations next. Nice job, John. So the question asks us to find two approximations. We want to find or approximate sine of 0.01. Okay. Now this one's a little bit easier than the last question because we don't actually have to change this value too much to figure out what we have to plug in. What am I plugging in for x to figure out sine of 0.01? 0.01, right? So L of 0.01, well, L is x, so it's got to be 0.01. Okay, so the approximation for what sine is at 0.01 is 0.01. Okay, now let's approximate sine of negative 0.01. Very easy this time too, because all we have to do is plug in negative 0.01. Okay, so plugging negative 0.01 gives me negative 0.01. Okay, now this is kind of strange to me actually, thinking about this. We started with sine of x, and we said the best approximation for sine is just x, or a straight line. Kind of weird, right? But if we kind of take a picture of this, we have our sine function here, and actually the value or the function y equals x does look like sine if we zoom really, really close in, right? The pink line looks very, very similar to my sine function. Now, as you zoom out, you can tell that x does not approximate sine very well anywhere else near zero, but for very, very small positive and small negative numbers, sine does look like the function. Okay, now one thing I do want to talk about real quick before we leave is I do want to show you something kind of cool. Okay, now this is a totally valid approximation, and I think if you ever go to grad school and meet some math grad students, they like to make fun of engineers because basically physicists use this approximation a lot. Okay, so a lot of times physicists will take sine, and instead of using sine, which is like a complicated trig function, they'll just use x instead. Okay, and as proof for this, I've actually taken this paper, this physics textbook paper, and this textbook shows the, it's basically a proof for like the period of a pendulum going back and forth. Okay, now there's a lot of lines here of math. I kind of want to focus on this line here, 24.1.14. This is a physicist writing this paper. We started with sine, and literally the next equation is saying, okay, I'm going to plug in theta instead of sine theta. So from here to here, they replaced sine with theta. Okay, now you might laugh at this. This is actually a total valid thing to do if we're looking at applications where the numbers are really small, but it is kind of funny, and this is what math people rag on physics people for doing, even though the math people create these approximations to begin with. But proof that this is actually useful in the real world. Okay, there is an optional example on the back. I have the answer at the bottom. I won't do this in class, but feel free to work on this if you want to. But other than that, I think we're pretty much done. I will see you on Wednesday, and we'll talk about something other than linear approximations.